Welcome to this explainer. Today we're diving straight into the invisible force that literally powers our modern world. I'm talking about electronics and communication engineering. Think about it. From the smartphone in your pocket to satellites orbiting Earth, right down to the 5G networks connecting us all. This is the branch of engineering that actually makes all of that possible. If you've ever wondered how on earth your video call reaches someone halfway across the globe in real time without skipping a beat, well, you are absolutely in the right place.
Okay, here's our roadmap for this explainer. 1. The invisible force. 2. The training ground. 3. The real world. 4. Future frontiers. And 5. The final verdict. Let's get right into it.
Section 1. The invisible force, powering the connected world.
So, what exactly is EC engineering anyway? Well, it's a discipline that brilliantly mashes up two really powerful areas. On the electronics side, you're getting your hands dirty with physical hardware. We're talking designing circuits, building microprocessors, and creating embedded systems. These are basically the hidden, tiny computers stuffed inside everyday things like your microwave or your car. Then, on the communication side, it's all about the science of transmitting information. It's figuring out how we take a massive 4K video, encode it into electromagnetic waves, and blast it wirelessly across space without losing a single pixel of quality. You're essentially building the bridge between cold, hard physical hardware and the invisible waves of data floating all around us.
To really wrap your head around the sheer scale of this field, just think about this number. Over 7 billion. There are literally more mobile phone subscriptions worldwide right now than there are people on Earth. And every single one of those connections, every late-night text, every movie you stream, relies entirely on the principles of a CE engineering. This isn't just some niche backroom field, you know? It is the absolute backbone of the modern era.
Section 2. The training ground, your 4-year curriculum.
So, how do you actually learn to do all this? Let's walk through how this builds, year by year. Year 1 is all about your foundation. You're tackling some heavy engineering math, semiconductor physics, and programming in C or C++. It's tough, but it builds the analytical tools you are definitely going to need later. By year 2, the specialization kicks in. You're learning network theory and digital logic design, which is basically figuring out how computers actually process information using just ones and zeros. Then, in year 3, you take a deep dive. This is where you get hands-on with microprocessors and VLSI. VLSI is the science of designing computer chips with millions of microscopic transistors. It's wild. Finally, in year 4, you apply everything to advanced tech, stuff like wireless communication and digital signal processing. This all wraps up in a massive 6 to 8 month capstone project where you get the ultimate thrill of building a working system totally from scratch.
Section 3. The real world, careers, salaries, and reality.
Now, what happens when you finally step out of the classroom and into the job market? Imagine a typical day for an embedded systems engineer. In the morning, right after a quick stand-up meeting, you might be playing the role of a hardware detective. You're using a logic analyzer to hunt down a really frustrating battery drain issue on, say, a smart home sensor. Then, in the afternoon, you pivot to the more creative stuff, coding cloud communication protocols and flashing new firmware. That's basically installing a brain onto the actual hardware to test it out. By late afternoon, you're updating documentation, maybe spending some time learning about new Bluetooth capabilities for your next big project. It really grounds all those abstract, heavy math concepts in a gritty, satisfying reality. You are literally making physical devices come to life.
And, you know, all that tedious hardware debugging definitely comes with some very real financial rewards. For entry-level engineers, particularly in top tech or semiconductor firms, starting salaries in India can range anywhere from 7 to up to 35 lakhs per annum. As you gain experience and move into a mid-level tech lead role, that jumps to a very solid 12 to 35 lakhs. And if you really stick with it, becoming a senior architect or VP with 8+ years of experience, you're looking at 30 lakhs to well over 2 crores, especially once you factor in stock options. It's one of those fields where highly specialized skills directly, and I mean directly, correlate to high earning potential.
But it's not just about the money. It's about the incredible diversity of industries you can jump into. You are absolutely not boxed into just one path here. You could be designing 5G infrastructure for telecom giants like Jio or Ericsson. Or you could be diving into VLSI chip design for semiconductor leaders like Intel or Qualcomm. Maybe you want to design the next-gen audio systems and cameras for Apple or Samsung. You could even pivot into the booming IoT sector or design advanced driver assistance systems for automotive companies like Tesla and Bosch. Your skill set is so versatile, you can easily pivot across these massive global sectors.
Section 4. Future frontiers,
AI, 6G, and beyond.
The landscape of electronics is shifting so incredibly fast, and there are some truly breathtaking innovations on the horizon right now. We're already seeing 6G research exploring terahertz systems. I mean, we're talking speeds that could actually enable real-time holographic communication. Then there's edge computing, which is pushing AI processing directly onto tiny, low-power IoT devices instead of relying on the cloud. And neuromorphic computing? That's building chips that literally mimic the physical structure of the human brain to process information with ultra efficiency. It's crazy! The boundaries of physics and engineering are just constantly being pushed here.
And of course, we have to talk about how the rise of AI is transforming the field. AI is starting to automate the routine tasks, things like repetitive testing or manual PCB routing, which is literally drawing out the electrical pathways on a circuit board. Because of that, those manual skills are becoming a bit less critical. But notice what's becoming way more important: system-level thinking, hardware AI integration, creative problem solving. AI is a tool, not a replacement. You still absolutely need an engineer to design the overall architecture, to debug physical constraints like heat and electromagnetic interference, and to figure out how to squeeze a massive AI model onto a tiny, resource-constrained chip.
Section 5. The final verdict. Is EC for you?
So let's weigh it all out with an honest reality check. On the advantages side, you get to build tangible products. You can actually hold what you make in your hands, which, trust me, is incredibly satisfying. Plus, physical hardware constraints just don't change as fast as software trends, which gives you some really long-lasting job security. But we've got to look at the challenges too. This branch requires physical lab work. You can't just code from your bed in your pajamas. There is a steep math learning curve. And tracking down a cold solder joint, which is basically a microscopic loose connection on a circuit board, can be incredibly tedious. You're always going to be working within these strict, frustrating limits of power, size, and cost.
So it really comes down to self-reflection. Ask yourself, do you naturally take devices apart just to see how they work on the inside? Are you willing to push through some really tough math and physics? Does the idea of building a physical gadget excite you way more than just writing pure software code on a screen? And maybe most importantly, do you actually have the patience to sit at a lab bench and systematically trace a bug with an oscilloscope for hours?
You really have to ask yourselves, is this actually right for me? Because EC isn't just some safe, default college major. It requires genuine passion. You're not going to become an expert overnight, and the learning curve is, quite frankly, demanding. But if you have that deep curiosity, if you're the kind of person who thrives right at that messy intersection of hardware and software, the rewards are absolutely unparalleled. I want to leave you with this final lingering thought. Will you be the one to build the physical infrastructure of our digital world? Because the connected world of tomorrow, the billions of smart devices, the autonomous cars, the practically unhackable networks, they all need engineers to actually build them. If you're ready to step up to the challenge, EC Engineering offers an incredible 40-year career adventure. Thanks so much for joining me for this explainer, and keep exploring.